The last topic we're going to look at with trees is the idea of a spanning tree. And a spanning tree is a tree that you can generate from a different graph that isn't necessarily a tree itself. So you start with a graph that it's not a tree, but a simple graph, and we can generate a tree from that, which is basically we remove edges that are superfluous. So we kind of find the simplest connected version of that graph by looking for the tree that relates to it. So it's a tree that contains all those vertices, but it doesn't have any superfluous edges. So for example, if you had a map like the one drawn here represented by this graph, and say you wanted to plow roads so that everyone could travel everywhere else, but you didn't want to plow all the roads, you could select certain ones that would still open up all the paths, but without having to plow everything. So, for example, you could do, if you do this by copying and pasting, you can delete some of these, like say this one here, and these here, and even this one here. That's one spanning tree. And so, of course, you can draw many variations of spanning trees for the same graph, but a spanning tree is one that spans the whole thing, meaning everything's still connected, but it's a tree, meaning there's no wasted effort. So you don't need the road between C and D to be plowed necessarily, because if you want to travel from C to D, you could still travel up, over, and down. A little bit less efficient, but if it saves you the time of plowing it or the resources that are limited, it might be a good thing. If you've seen, for instance, as you're driving down the road, you see those roads that are designated as emergency evacuation routes and things like that. It's because someone's gone through and planned out a map like this of how to focus on a few roads that will free up or give people the ability to move around without having to account for every road that's out there, because that would be just unfeasible. So it's one example of an application of a spanning tree. Of course, there are many others. You can think of communication networks. You might want to find the most efficient way to communicate, to distribute data. So you'd look at your network topology, you'd look at your graph that represents your network, and then look for a spanning tree to shorten the number of connections you need to maintain, and so on. So there's all sorts of applications of this. We'll talk about a couple of ways to find a spanning tree, and it won't take us too long to find an easy way of doing this. So there are two ways we're going to talk about to find a spanning tree. One is called a depth-first search. The other is going to be called a breadth-first search, and we'll see that later, a little bit later. So the idea of a depth-first search, and this is a general term that applies to searching algorithms in general. A depth-first search basically drills down as far as it can and keeps going in the same direction until it hits a dead end, and then backs up and continues on. So this would be like if you were searching for something and you just picked up the first encyclopedia you found and read through the whole first encyclopedia, and then picked up the second encyclopedia and read through all that completely. Versus a breadth-first search, which would be more like looking at the index of each encyclopedia and getting a sense of what's in there, and then coming back to it as needed. So depth first sort of drills down in one topic or one place as far as it can before backing up and starting in a different place. A breadth first search gets sort of an overall view first and kind of travels down one layer at a time. That's kind of a rough description of the two. So the depth first search, in both of these, we're going to start with an arbitrary place, and we're going to start with F. I just picked it because it's kind of in the middle of the graph, but there's no other significance to it. You can pick any one of these as your starting point. And this is going to be kind of the root of our tree in that sense, even though this spanning tree is not actually a rooted tree, but or doesn't need to be a rooted tree, I guess. But you can still think of it in that same way. So you start with an arbitrary vertex, so I'll pick F, and then you're going to take a path from there in any direction you like, until you hit a dead end. In other words, until you hit a node that doesn't have anywhere else to go. So let's say I go from F to G to H to I to J to K. Now at this point I've hit a dead end because there's nowhere else to go from K that I haven't already visited. So I'll stop there, and then from there you'd kind of back up until you have somewhere else to go. So I'd back up to J. Is there anywhere else to go from J that I haven't already gone? No. Back up to I, same thing. Back up to H, same thing. Back up to G, same thing. And then go back to F and start again. So basically what I'm doing here is I'm building a tree where from F I can go down to G, and then to H, and then to I, and then to J, and then to K. And then back at F, I can go, let's say I go to E, and then to C, and then to B. Now there's a dead end, right? So I've hit from F, I went to E, to C, to B, hit a dead end. So now I back up, and I go back up to C. Is there anywhere to go from C that I haven't gone yet? Well, I can go up here to A, and then from A I can go over to D. So there's that spanning tree. Now I'm going to redraw the tree in a way that looks more like the tree we've drawn. In other words, I'm going to draw this spanning tree over the one we already have, just to sort of visualize it a little bit better. But remember, with the graph or with a tree, the way we draw it is not significant. All that matters is what nodes are connected to each other. So here's the original version. Sorry, there were, well, let me do it this way. Just to show you how it works. So from F, I can go down to G, and then over to H, then up to I, up to J, and up to K. So all I'm doing is traveling down that branch of the tree. And then F is also connected to E. E is connected to C, which is connected to B, and then to A, which is connected to D. So it looks like that. And if I start erasing the pieces that are not part of this, there's our spanning tree. And again, you could draw many different variations of a spanning tree for the same graph, but that's one example. And this one was done with this depth-first search. So you can kind of see how from F there's these two long stretches that go out from that in either direction and sort of curl around as needed. So that's one way to find a spanning tree, is just to go from your arbitrary place and just take a path in any direction you like until you hit a dead end, and then back up and keep backing up until you have somewhere else to go. The other option is to take a breadth-first search, which is start with one vertex again, so we're going to start with F, and add all the neighbors of that one. So this one has neighbors at D, at E, at G, and at H. That's 4 neighbors. And then you step down to the next one and keep doing this. So D, we've already accounted for E, so we don't need to include that one. So the only remaining one is A. Then we go over to E. We've already accounted for F and D, so all that's left is C. And then at the end of C, all that's left is B, because we've already accounted for A. Then we go over to G and repeat this. So G's neighbors are F and H, but we've already accounted for F. So we'll just have H. Oh wait, we've already accounted for H too. Never mind. So H has neighbors at I and K. And whichever one of them we choose, we can have the neighbor at J. Again, it's a little bit arbitrary how we do this, but once we do, we should get something. Again, let me draw it over the previous one. So here we've got from F, we go out to G, to H, to E, and to D. From D, we go to A. From E, we go to C, and then B. And then from H, we go up to I, and over to K. And from I, we go to J. So we can delete, again, any edges that are not required to make this tree. So if you look at the two examples of spanning trees we drew, you can kind of see the difference in the way they're drawn, the breadth first versus depth first. Breadth first kind of has this more webbed look to it, where you branch out in sort of even branches in each direction, versus the depth first, which tends to have those long stretches that come out from the center. But either way you do it, you've got a spanning tree. It's not hard to draw one, but we've just seen two ways to do them. And again, there are applications of spanning trees, including things like communication networks or travel networks or things like that. If an airline, for instance, wanted to eliminate some routes to simplify their process but still connect everybody, they could look for a spanning tree and so on. So there's all sorts of applications of those. So that brings us to the end of our study of trees and really the end of our study of graph theory in general as well.